So let's have a quick show of hands to get a feel for the audience. So who here uses Java? Okay, that's good. Who has tried the early access builds of JDK 8? Okay, a few people. Who has tried Lambda expressions? It's probably the same people. That's okay, good. Who's using Java SE7 in production? Good. Who's using Java SE6 in production? Fine. Who's using Java SE5 in production? Okay, one or two people. Anybody using anything older than Java SE5? Very good. That's what I like to see. So James gave us a very interesting presentation around why Java, in his opinion, has got its mojo back. And I certainly agree with that, not just because I work for Oracle, and so my job depends on it. But I think that's absolutely right. I think that we see a lot of people in a lot of different situations who are using Java and kind of looking at other alternatives and still coming back to Java. What we at Oracle want to do, certainly from the perspective of the Java platform, is to make life easier for you as developers. We want to make it so that there are things that you might not be able to do so easily at the moment, you can now do more easily as we evolve the language. And so that's really what I'm going to talk about in this presentation, is the specific feature of JDK 8, Java SE8, which is Lambda expressions. And I want you to understand what they are, why they're so important, and how you can use them in terms of developing software and making it easier to do the kind of things that you're going to need to do. So my first slide is always the usual legal slide that you get from Oracle. Basically, that just says don't base any purchasing decisions on what I'm telling you. Thankfully, we give Java away in terms of the JDK and the Java runtime for free, so it doesn't really have too much bearing on that. But I have to put that up. They tell me I have to put it up. I've given you time to read it. So let's start with a little bit of background around the idea of Lambda expressions and why we need them and what they're for and so on. Now, the reality is today that, as for the last 40 years, we've had Moore's law. So Moore's law has said that the number of transistors that you can squeeze into the same size piece of silicon doubles roughly every 18 months to 2 years. And up until about 2005, 2006, we kind of equated that with a doubling of computing power based on not just an increase in the number of transistors, but also an increase in clock speed. And so you saw more powerful processors every sort of couple of years, and clock speed meant that it got more and more powerful. What we've now done is we've reached that kind of limit in terms of cooling using air. So we get to about 3 to 4 gigahertz, and the amount of power that gets dissipated by your processor becomes so high that you start needing to use something other than air to cool it. So what the chip designers have done is they've switched away from the idea of simply increasing clock speed and increasing the complexity of the processor itself into the idea of multi-core processors, something I'm sure we're all familiar with. So nowadays, my laptop has 4 cores in its processor. Mobile phones have 2 cores quite frequently. Tablets have 4 cores or 5 cores even, depending on what you're using. But the reality is that as we move forward, we're seeing more and more multi-core programming. It's not just about big servers having lots and lots of processors. It's about tablets, it's about laptops, desktops. Everything has multi-core processors. The significance of that is that when it comes to programming and developing applications, you need to be able to develop applications that can work truly in parallel. We're not relying on time slicing and time-sharing operating systems to make it look like you do things in parallel. Now you really do things in parallel. So we have to adapt the way that we program in order to allow us to get the most out of the processors that we've got. And this comes back to what James was saying about scaling. If we want Java to scale, it's got to be able to run application code in parallel. So if we look at the kind of history of Java, Java has always had the concept of multi-processor support. We've always had the concepts of threads built into the language, right from the very, very beginning. Now, the thing is that with the thread class, if you look at it in detail, what you'll find is that it's fairly simplistic in terms of the approach that it gives you for writing multi-threaded code. So you've got 4 methods in there which allow you to coordinate different threads. You've got sleep, you've got wait, you've got notify, and you've got interrupt. That's all very well and good, but those basic methods mean that you end up writing very, very complex code, and it's very, very difficult to write reliable code using those methods. And in fact, if you look at the thread class as well, there's some sort of design flaws in there, which means that several of the methods in the thread class are actually deprecated as being thread unsafe. So, we have to deal with that. What we did in terms of the evolution of Java was we said back in Java SE 5, we need better ways of writing parallel code. We created the concurrency utilities. That was a lot of work that was done, JSR 166. And what that allowed you to do was to use more familiar concepts in terms of the API. So we had the idea of read-write locks. We had the idea of reentrant locks. There were classes for things like semaphores, which are well understood concepts in terms of writing concurrent applications. And that made it a lot easier to write reliable multi-threaded code. Java SE 6, we tweaked the libraries a little bit. We added a few new features, a few new APIs, some more complex things like phasers, which gave you the ability to do different kind of concurrent application code and so on. And then in Java SE 7, we introduced the idea of the fork join framework. Again, let's take an API and let's make it easier for you to take specific types of tasks and make them run in parallel. So the fork join framework takes a task which can be split up into subtasks, and those subtasks don't really share data. And that's one of the key things. You don't really want those subtasks to share data. And the framework will assign threads to those subtasks. You can do it recursively, and you can break up the task into a level of granularity, which means that you've got small enough tasks to execute in a single thread. The framework does all of the thread pooling, it does all of the synchronization for you, and then when all the tasks are finished, it brings all the results back together and out-pops your result at the end. So it does make life a lot easier for certain types of multi-threaded application again. But we still need to go further. And what we're doing in Java SE 8 is introducing Lambda expressions. And a large part of that is to make it simpler to write multi-threaded code. Now, in terms of the approach that we're taking for how to make your life as developers easier for this idea of using multiple cores and multiple processors, is to take the hard work and put it into library code. So what we really need are libraries that will do the difficult stuff for you. So you say, okay, here's my task, here's what I actually want to do, give it to a particular library, and the library does all of the stuff for you. And that's what we're really targeting, is moving the code away from you having to do all of the boilerplate code, dealing with threads individually and dealing with concurrency and locking and all those types of things, and say, let's just push it into the libraries, make it easier for you that way. And fundamental to that is the idea that if you look at the way we code at the moment, if you write a particular piece of code, you will find that at the moment, you tend to write either in a sequential way or in a parallel way. So there's different approaches based on how you actually want the code to work. What we'd like to do is to remove that distinction. So you simply say, I want something to happen, you write the code for how that's going to happen, and how that actually gets implemented underneath can be either sequential or parallel. But it's not up to the way you've coded it to tie it to a particular thing in that respect. Now, we can do that a lot in terms of the library code. So we can create these new libraries, we can simplify things through that. But it's not enough to simply add more APIs into the class libraries. At this point, to make life simpler and to really implement this in the best possible way, we also have to change the language syntax itself. We have to make some fundamental changes to Java that will allow us to do this. So that's where Lambda expressions come in. So let's look at Lambda expressions in Java. So here I've got a very simple, very common piece of code that we might develop as a Java application developer. So what I want to do here is I want to have a collection of data. We often have collections of data that we need to process in some way, searching for things, sorting things. These are all very, very common tasks. So I have my collection of data, and in this case it's going to be a collection of students. So I create myself a list, I use generics to type it as a collection of students, and then I create that list to store my objects in. Now what I want to do with this is I want to search through it, and I want to find the student, or at least the highest score that any student got in a particular year. So again, simple task, and I can do that in Java using this kind of idea. So I say, okay, I'll create myself an instance variable, high score, assign it 0 as its initial value, and then I'll iterate through my collection. So I use the new, Java SE5 new, for each construct in order to iterate over the collection. And then for each element in that collection, I compare the score against my highest score, and if it's greater than that, then I record it in the highest score. It's very simple, very straightforward. It works. Absolutely nothing wrong with that code at all. It will work 100% of the time. The problem is that this is inherently serial code. And Guy Steele did a very good presentation where he sort of looked at this type of code, and he spent a lot of time explaining all the intricate problems that you run into. And it is because we, as the client, are controlling the iteration. So we have our for loop in there, which is doing the iteration. And because we have an instance variable, highest score, we are making it inherently single-threaded. We are making it not thread safe, because if you wanted to have multiple threads dealing with this loop, you have your single instance variable, which then needs to be updated by multiple threads, potentially in parallel, which requires locking. Now, there's all sorts of techniques you can use to get around that. You can, assign a variable to each of the threads and then, look at that when you've got all your results at the end. But that only works in certain situations. So the code itself is inherently serial. We're controlling the iteration, and it's not thread safe. So this is not a good way of trying to make your code parallel, because you can't make this parallel in this form. So what we can do is we can take a different approach. We can use a different part of the Java syntax, and we can say, well, let's make it a little bit more functional in its approach. Rather than having the idea of us controlling the iteration, what we'll do is we'll take a sequence of methods and we'll call them in a chain. So it's more of a sort of fluent API, where you're taking the results from one method, passing it directly to another method, and then passing those results further down the line. So we end up with what we have here, where again we've got our list of students, and now we can simply say the result of this is the result of calling a sequence of methods. So the methods are going to be filter, map, and max. Now, in order to make these flexible so that we're not tying them into a specific set of code, what we need to be able to do is we need to be able to say, okay, what is the filter going to do? What is the map going to do? And the way that we commonly do this in Java is using anonymous inner classes. Anonymous inner classes, for want of a better word, are a kludge. We introduced them way back in 1.1 as a way of allowing us to do this kind of thing. So we have our filter method, and that takes an object of a particular type of interface. So in this case, it's a predicate interface, and it has a type parameter associated with it for student. And then we have to implement, using our anonymous inner class, the method op. And for that, we simply return whether the graduation year equals 2011 or not. So it returns a Boolean to indicate whether we got success or failure. Then we pass the results of that set of operations onto the map. And again, we use an anonymous inner class because we're passing in an object which implements a particular interface. Interface in this case is mapper, and this takes two type parameters. What we then do is we implement the extract method of that, and we say, okay, what do we want to extract? We extract the score. Then we pass those results into a max method, and we get out the result that we want. So the thing about this is it is no longer inherently serial. So we could, if we wanted to, implement the way these methods work in a parallel way, because we're passing data from one to the other, so we could do that potentially in parallel. So the way we've written the code now no longer means it is definitely going to be serial. We could do it in serial form, or we could do it in parallel. So we're no longer controlling directly the iteration over the collection ourselves. We're not inherently serial. We can traverse it in whichever way we want to. We can use lazy evaluation. We can apply a whole different set of techniques in order to make our code more efficient. But there is a problem with this. And the big problem with this is it's really nasty to look at. So the code is just plain ugly. I mean, you're implementing anonymous inner classes, which means you've got to define, okay, I want a new instance of this particular interface. I've got to define this method. And there's a lot of signal, or a lot of noise to signal in this. So what I've done here is I've highlighted in red the bits that we're actually interested in. So we want to filter based on the graduation year being 2011. We want to map in terms of the score of those students, and then we want to get the max result from that. So Lambda expressions allow us to simplify this code. And we can do it using a Lambda expression in this way. So now, we don't have to have this anonymous inner class construct where we're saying, okay, new instance of the filter, implementing this, providing the implementation of the method op, and so on. What we now do is we pass in a Lambda expression. A Lambda expression looks like a method in some ways. So we've got a Lambda expression which we're passing to the filter. And the left-hand side of the arrow you can think of as being the parameters to your method. In this case, student S. The right-hand side of the arrow you can think of as the body of your method. So in this case, we have s.grad year is equivalent to 2011. Now, you will see that it doesn't look exactly like a method because it doesn't have a method structure to it in the way that we expect it to. It also doesn't have an explicit return. So the body of the method simply says s.grad year equals 2011. So the compiler will determine from that the return type of this Lambda expression must be a Boolean, because that's all that you can get from that particular piece of code. Similarly, when we use the Lambda expression for the map, we're passing in a student S as our parameter, the method parameter, and then the body of the method, if you like, is to return the score of that student. And again, there's no explicit return. The compiler will infer from that the type of the return value is going to be, well, it could be an int, could be a double, whatever get score returns in terms of its type. Now, if you want to, you can put explicit return statements in there. So there's nothing wrong with creating a block of code. You can use braces. You can put quite complex code into your Lambda expression and have it look like a proper method body. And you can have multiple returns from there. And again, if you do that, the compiler will infer from that what is the appropriate return type for your Lambda expression. So this now becomes a lot more readable. It's a lot simpler in terms of the code that we're looking at. It becomes more abstract in the sense that we're now saying, okay, Lambda expression indicates what the functionality is that we want to happen in that case, and we can look at that and we can understand what's going on. It's less error prone because with having a lot less code, you can see very clearly what's going on in terms of this. Again, no reliance on mutable state, so it becomes thread safe and becomes easy to make it parallel. And we'll come back to that as we talk a little bit more about some of the things that we can do around that. So let's look at some of the more detailed aspects of Lambda expressions. The important thing to understand about a Lambda expression is it is an anonymous function. So it looks like a method, but it's not a method. So I'm going to come back to this, and it's a very subtle and important distinction to make. It does look a lot like a method, it behaves a lot like a method, but it is not a method in the true sense. It is a function. And like I say, I will explain a bit more about that as we go through. So the things that it has in common with a method is that it does have a typed argument list. So you can pass in no arguments, you can pass in one, you can pass in multiple arguments, and they have types associated with them. It has a return type associated with it in exactly the same way that a method does. And it can also have thrown exceptions in the same way that a method can. And it has a body of statements that are to be executed. So all of these things make it look exactly like a method. But from the point of view of what we're talking about here, we are actually saying it is an anonymous function. Now, from the point of view of typing, what we're doing is we're passing something to a method in the examples that I used. So we have a Lambda expression, and we pass it to a method. What is the type of that thing that we're passing to that method? Now, if you think about the way that we define a method call will have a parameter defined for it, which will be of a particular type. And frequently, what we will use for this kind of thing is an interface. So we say the interface we're going to use is predicate or mapper, and that will define a method. But now, in the case of the Lambda expression, we are saying this is actually a functional interface. It's kind of a new type in terms of Java, not from explicit types in terms of the way that we program with Java. This is more of an implicit type that you get in terms of the way things are implemented underneath. So what we have is a functional interface, and this is different to a class. And this is why the Lambda expression looks like a method but is not a method. A method in Java is associated with a class, and that's how we resolve a particular method. So we know what classes are loaded, we know what the method signature is. When we want to resolve that method, we define which method we're going to call based on its signature and the class is loaded. In the case of a Lambda expression, what we're dealing with is a functional interface, an anonymous function. So it's kind of like a method, but not associated with a class, which is why I say it's not a true method. So the functional interface itself is identified structurally. And what that means is that the compiler will figure out from what you've put in your Lambda expression what the functional interface type is, and which Lambda expression it actually ties into. So the fact that we have a type of a functional interface is very important. And we have to remember that. We will come back to that as we talk about some more of the details. And if you look at the way that we have what are called single abstract method types that we use a lot in Java at the moment, this is how we can replace those single abstract method types with a Lambda expression. A Lambda expression, by definition, can always be used where a single abstract method type is used. So if you look at things like runnable, that has a single method run. If you look at action listener, that has a single method action performed. Callable has call, and so on. So these are single abstract method types. Wherever you use a single abstract method type, you can replace it with a Lambda expression. Similarly, wherever you could use an anonymous inner class, you can replace that with a Lambda expression. And although I don't have time to go into all the details of this today, the way that we implement these things is not simply through what's called syntactic sugar. We don't simply say, well, if you can replace an anonymous inner class with a Lambda expression, then what we can get the compiler to do is to simply take a Lambda expression, replace it with the equivalent anonymous inner class, and then compile that as if it was pre-Java SE8 code. What we actually do is we use the invokedynamic bytecode that was introduced in Java SE7 so that we can decide at runtime how we want to implement the way that the Lambda expression is implemented. And that way we can actually get better performance in terms of using Lambda expressions than we can, well, potentially we can get better performance than we can with using anonymous inner classes. Target typing is quite important. So what we need to do here is we need to say, okay, Lambda expression is a way that we can create an instance of a functional interface. And as I said, the compiler will figure out from the way that we define our Lambda expression which functional interface it actually equates to. Because you don't define that in your Lambda expression. You define the parameters that are being passed to the Lambda expression. You define what happens in that Lambda expression which the compiler will then infer what the return type is from that. Using the parameters and the type, using the return type, the compiler can then figure out what interface does that relate to, what does it match, and so what is it that that Lambda expression actually represents. So we can do that both in assignment and also where we actually use the Lambda expression. We'll come back to this later when we talk about some more examples of how we use that. But essentially what we can do is we can say, okay, rather than using anonymous in a class here, where we're creating a comparator, a type string, and we call compare, we simply call or we can assign the Lambda expression to a reference to a comparator of type string. And then we can use that wherever we want to. So we could use C wherever we want to use that Lambda expression. Local variable capture. So one of the drawbacks of anonymous inner classes is the fact that if you want to access a variable from outside of the anonymous inner class in your class, your anonymous inner class, then it must be marked as final. And so if you've used anonymous inner classes, you know that that's one of those things that always tends to catch you out because you have to go back and mark things final and figure out how to get around that problem. So Lambda expressions are not closures in the sense that other languages implement closures. And one of the things which means they are not full closures is the fact that we can't capture non-final variables in terms of Lambda expression use. What we have done, though, is to make your life a little bit easier. So Lambda expressions now are allowed to use effectively final local variables. That means that you don't explicitly have to mark a variable as being final, but if you use it within your Lambda expression, then it has to behave as if it is marked as final, which means you can assign a value to it once, but you cannot then change it afterwards. So if you try and do that, if you try and use a variable where you're modifying the variable in other parts of your code, then you will get a compiler error. So you can, in this case, I've got this method here where I'm passing in a variable called before, and then I'm using that within my Lambda expression to test against a modification date. Although I haven't marked before as being a final variable, I can still use it legitimately because in this code I'm not changing it, and so it behaves as if it was final. There's also the concept of lexical scoping, because in a method you can refer to this meaning the class which a method is associated with. In a Lambda expression you can still use this, but, and this is where the fact that the Lambda expression is not associated with a class becomes significant. It is an anonymous function. If you refer to this in your Lambda expression, what you're actually referring to is the this of the outer method, so the code which surrounds the Lambda expression. So the Lambda expression does not refer to any object which is associated with the Lambda expression itself. It's associated with the outer code, the outer method or body or whatever. So you need to be aware of that. This is, like I say, where the distinction of a Lambda expression not being a method and not being associated with a class becomes significant. Now, the other thing that we can do with Lambda expressions is we can do type inference. So the compiler can use the fact that it knows about some of the types that are being used in things to allow you to not have to specify the types wherever you actually have to use them. So for example, if I'm doing a collection sort on something, then my Lambda expression might be taking 2 strings as input parameters and then returning the difference in the length of those strings. In this case, because the collection type is known by the compiler, because I've used generics and therefore it has a type parameter associated with it, what I can then do is I can simply say x and y, not explicitly stating that they're strings because they can only be strings because the collection is of type string. So the compiler will then say, yes, x and y must be strings because the collection is string, and it will fill that information in for you. So it will infer the types for you. So we end up with type inference based on the target functional interfaces method signature. So this is, again, where you have to kind of get your head around this a little bit, is understanding that when you use this Lambda expression, the compiler will look at that and it will say, okay, ls is a collection of type string, therefore the parameters x and y must also be of type string. It will then determine from that the return type being a value which is an integer, and therefore it will determine what the appropriate functional interface is, which matches having two strings as input and an integer as a return value. What we end up with is the idea of more typing with less typing. So this is the sort of typing joke. So we end up with stronger typing, but with less actual typing on the keyboard. And the important thing to remember about this is it does not allow dynamic typing to sneak in. So we do not want dynamic typing in Java. It's fully statically typed. This is good. And yes, we can have that conversation about typing and whether static typing is good versus dynamic typing. Me, I'm a static typing person. Right. Now, the other thing we can do is we can say, okay, let's use a Lambda expression to replace something like this. So here I've got a filter. I'm going to use a file filter, and I've got an anonymous inner class which simply returns whether I can read a particular type of file, a particular file that I'm passing. So I can replace that with a Lambda expression where I can say file filter x equals file f being the input parameter and can read as being the method called on f and returning that value. To make that even simpler, we've introduced another shorthand, which is the idea of a method reference. So now you can simply say file filter x equals file : can read, and that will equate to the same Lambda expression that you have above. And I'll show you some examples later on of how we can actually use that. And how Lambda expressions do need to be thought about a little bit when you're actually using them, because sometimes you look at the code and you go, oh yes, we'll make it nice and succinct, and we'll make it really short, and we'll make the code simple. But it isn't always necessarily simple in the sense of like when somebody else comes to it and then goes, ooh, what's it actually doing? So there are some things that you need to be a little bit careful about. Now, the other thing we can do is we can do a constructor reference. So here I've got an interface which I've defined, a factory interface which takes a method parameter type t and returns something of type t when you call make. And what I can do is I can say, okay, I want to define a Lambda expression which will allow me to do that. And I can say, okay, factory list, which generates a list of type string, f is going to be an array list of type string, : new. And that will reference the constructor of the array list of type string. And that's equivalent to a Lambda expression which is the same as this. So we're saying, okay, the Lambda expression is the same as having no arguments because we just want to create something, and then the body of the Lambda expression is to return a new instance of array list of type string. But again, shorthand that we can use to make our code simpler and hopefully easier to understand. So Lambda expressions in Java are really about giving you a tool to really simplify the way that we can specify, the way that we can process data. So it allows us to replace the use of anonymous inner classes. We can use single abstract method types. We can make life a lot simpler in terms of libraries, because now we can use this idea of passing or having chained method calls where we pass in interfaces which are the definition of what we actually want to do, and we can use Lambda expressions to do that in a simpler way rather than using anonymous inner classes. That way, we're going away from the distinction between serial and parallel coding. We're just saying, use this way of doing things, and then how it gets implemented can be either serial or can be parallel. And as we've said in the past, adding Lambda expressions to Java is not a revolutionary idea. It's pretty much the last major language to add this kind of feature to it. So let's talk a little bit about library evolution, because having Lambda expressions is not enough. It gives us the basic building block of what we need, but if we're going to make life easier for you as developers, we need to then use Lambda expressions and build on top of that to give us the more complexity and more powerful features that we need. Now, in terms of evolving the libraries, there are a number of significant challenges that we need to face. And one of the things is that if we just added Lambda expressions and we didn't change any of the libraries in the core class libraries, it wouldn't really be much use. If we just said to you, great, you can go off and you can use Lambda expressions and you can replace the places where you use anonymous inner classes, well, that's great, but it doesn't buy you a whole lot. So what we need to do is we need to say, okay, let's use Lambda expressions, let's figure out how to make them as powerful as possible by changing the APIs that we have at the moment. A lot of the collections API is built on interfaces. So we need to figure out how to use that kind of concept, single abstract method types, Lambda expressions, and so on. And certainly if we had Lambda expressions when we first started developing Java, the libraries themselves would look very different to the way that they do today. We would have designed them differently. We would have used the power of Lambda expressions from the very beginning. So what we want is some way of having collections with operations available on them which allow us to do aggregate type of operations. Sorting, searching, doing something which affects the whole collection, going through the whole collection, finding things, and so on. So these well-known ideas, filter, map, reduce, fundamental sort of algorithm, fundamental way of doing things, is what we want to be able to implement. We want to be able to take these kind of concepts and do them. And then we also want them to be able to run in parallel just as easily as run them in a serial function or a serial way. So what we need to do is figure out how do we do that? How do we add new methods to interfaces in the Java APIs? Because the huge problem that we face with that is saying, well, okay, if I've got a collection API, collection interface, and I've implemented that in Java in the past, okay, I've got my class, I've got my jar file, all good stuff. Along comes Oracle and they say, we're going to add some fancy new APIs to this interface to make it really good and make it a lot powerful. Problem is that if you then try and use those APIs, use those new methods in the interface with your old class, then it's going to break because there is no, let's say, map method in your implementation. So when the compiler tries to use that map method, it tries to resolve it, boom, it fails. That could be even worse. It could be at runtime. You could be trying to resolve it. Nothing there. It fails. So that breaks backwards compatibility in a pretty significant way. And one of the things that we've always been concerned about when we were at Sun, when we were at Oracle, is backwards compatibility of Java. People like to know that they can take the same code they compiled with the 1.0 compiler and they can run it on Java SE8. It will work unchanged. So this needs to be addressed. How do we add new APIs to existing interfaces without breaking backwards compatibility? Well, the solution is virtual extension methods, or sometimes referred to as defender methods, depending on what language you come from. So what we do now is we say, okay, in our interface, what we'll do is we'll say, okay, we've got these methods, and then where we want to add new ones, we will define a method, and then we will also say that it has a default implementation, so that if your old class, which doesn't have map or sort or whatever in it, when the compiler or the runtime tries to resolve that particular method, rather than saying, well, it doesn't exist in your class, what it will do is it will go, oh, there's a default. So we'll go to the collections utility class and we'll call the sort method on that. And that will give us a generic default way of doing things. So that avoids the problems of breaking backwards compatibility. So we now have the ability to provide a default implementation within our interface definition. So I see people smiling, I see people chuckling about this and going, oh yes, that looks interesting, but I'm sure there's some drawback to this. Well, of course, some people might say, well, stop right there, because surely if you're introducing behavior into an interface by using a default, then you're sneaking in multiple inheritance. Somehow you're getting multiple inheritance into Java. And it's like, no, we don't want multiple inheritance in Java. Multiple inheritance is, well, from my point of view, I don't like multiple inheritance, so we'll keep it out of the language. So Are we introducing multiple inheritance? Well, yes and no. So yes, in the sense that Java already has multiple inheritance. The fact that we have interfaces means that we have multiple inheritance of types in Java. You can extend a class and then you can implement multiple interfaces, which means that you have multiple types associated with your class. So there is multiple inheritance of types already. What we're doing now is we're introducing multiple inheritance of behavior as well as multiple inheritance of types. So if you have your interface which has some behavior in it, then you're not only extending your method which has behavior in it, you're also implementing a method which has behavior in it, and therefore you've got multiple inheritance of behavior. What we're not doing is introducing multiple inheritance of state, and that's where all the real problems come with multiple inheritance. Now, that's not to say that there aren't a few things that you need to be aware of with using default methods, because of course, if you implement multiple interfaces, and let's say you've got a map method defined in your interface with a default, and another interface that you define also has a map interface, a map method with a default, when the compiler comes to compile or the runtime comes to resolve this, how does it know which one to use? Does it use interface A or does it use interface B? They both have a map method with a default, different defaults, which one does it use? Well, the answer is that the compiler will do its absolute best to decide which one to use. So long as it can differentiate between the two interfaces and the two methods based on their signature, then it will do. But if you end up with a situation where interface A and interface B both have default implementations of the same method with the same signature, the compiler will say, I can't decide, you have to figure it out. So it will say, it's not possible to compile this code unless you sort out the problems with resolving this. So you will get compiler errors if you get to that situation. But it does solve the problem of backwards compatibility in extending interfaces in Java. So the functional interface, as we've already seen, functional interface is basically somewhere where we can replace it with a single abstract method type. So wherever we use a single abstract method type at the moment, we can use a Lambda expression because it is a functional interface. Functional interface is one that has one abstract method. Now that might seem like a very simple definition, but there are actually situations where, again, the Lambda expressions can get a little bit complicated in terms of some of the fine details, shall we say. So if your interface has a single abstract method, then you're fine. But it doesn't mean it only has one method. You can actually have more than one method, as long as only one of them is abstract. And I found this because I was looking at some of the code in the class libraries, and I found this particular interface, and it was like, well, that's got more than one method, but only one of them is abstract. And so it can be a little bit tricky to sort of figure out exactly what that means. Similarly, one of the questions I got a while back is, well, okay, if I have something which is only a single abstract method, then can I not define an abstract class which has a single method which is abstract and use that? Well, the answer is no. We don't use abstract, although we define it as a single abstract method type, we don't use abstract classes to implement those things. So it has to be an interface rather than abstract class with a single abstract method. We might consider those at some point later, but for Java SE 8, we're not using abstract classes. We also have the idea of annotation to make life simpler. So if you believe that your interface is a single abstract method type and could be used for Lambda expressions, then you can mark it as a functional interface using the annotation, and then the compiler will check that for you. And so if the compiler goes through and it says, yep, that matches the requirements, all fine. If it doesn't, you'll get a warning saying, you define this as a functional interface, but it doesn't have a single abstract method associated with it. Which brings us to the idea of the stream class. And as I say, the real power of Lambda expressions is when you start building on top of them and using the libraries and adding things to the libraries. So the stream class is all about providing a stream of values. It's a bit like an iterator, but an iterator with a lot more functionality. So an iterator on steroids, if you like. And what it allows you to do is to say, I want this to happen either in serial or in parallel. Again, removing the distinction between serial type of coding and parallel coding, and we say, okay, if I want to get a stream of something, I can say, go, give me a stream from collection, or give me a parallel stream that will allow me to do things in parallel. And then I can say, okay, I've got my list of names here, which has got Bob, Alice, and Charlie in it. And then what I'm going to do is I'm going to print out the names, but I'm going to use a sequence of method calls in order to determine what's actually going to get printed out. So on my names list, I'm going to call stream to get me a stream of values from that, which is effectively like iterating over it, but not explicitly. Then I'm going to pass that to a filter to look for things which are greater than 4 characters in length. I use a Lambda expression to define how that filter works. So as long as the length is greater than 4, and then I'm going to pass that to find first. So this is where we can do lazy evaluation, because if I had 1,000,000 elements in my collection, rather than having to go through each of them looking for ones which were greater than 4 characters in length, I can actually say, okay, if it's got greater than 4 characters in length, when I get to the first one in that stream, stop right there, print out the result. So I'm actually only evaluating the first, what would it be, 2 elements rather than all 1,000,000. So that's the kind of thing where we get advantages, because we can do not just in parallel, we can do lazy evaluation, and we can stop when we get to the results that we want. And so we're not having to have all the results of stream passed to filter, waiting for all the results of filter to be passed to find first. It will pass results as it generates them. And so in terms of the stream package, this is a new package that's been introduced in Java SE 8. This is all about the stream interface. There's also a thing called a collector, which is again possibly a parallel reduction operation where you're converting from things of type T into results of type R. And so it's an interface which you can use if you want to convert things from one type to another based on a Lambda expression, which determines how that actually happens. So you can get things like string concatenation, minimum values, maximum values, and so on. Then we have the function package, and this is really where we see how Lambda expressions come into being able to use functional type programming in Java. So we have a number of interfaces that are defined in that. So there's like predicate, which will determine if the input that you're passing based on your Lambda expression matches, of type T, matches some kind of criteria. And then you've got a consumer of type T, which will accept a single input argument of type T and return no result. Don't worry about the details of that. I'm going to show you an example in a moment as how that works. And similarly, you've got a function which will apply a function on an input object of type T and return something of type R using a Lambda expression to define how that happens. And there's a whole bunch more in that particular package. So there's a lot of really useful interfaces that you can use with Lambda expressions. So let's look at that, how we put these Lambda expressions together with these new classes into making some useful and flexible code. So again, here's a simple bit of Java code. So I've got a class which represents a person. In that, I've got an enumeration for the gender, male and female. I've got some properties associated with that person, their name, their birthday, their gender, their email address, and so on. And then I've got some methods which allow me to get access to the different fields, and I can print out whole person information as a string kind of thing. And then what I'm going to do is I'm going to create a collection of that called membership. So this is what we're going to work with, is our collection of person objects called membership. Now, if I want to write Java code and I'm a fresh out of university person, don't really know a lot about how to write Java code, and I've not got a lot of experience, what I might do is end up with something like this. I need to find specific types of people. So in this case, I'm looking for people older than a certain age. So I write myself a method. So I've got my method, print people older than, takes as parameters a list of type person and an age which we're going to compare against, and then we iterate over it and we say if the age of the person is greater than age, print that person out. Fine, that works. Nothing wrong with it. And if we want to do the same thing where we now want to check for people who are younger than a certain age, then we write another method, takes same parameters, but this time does something different internally. And we can go on and on and on. So this is a bad approach in terms of a design because, of course, every time we want to add some new way of doing something, we've got to go in and modify the code, add new methods, use those methods in different places, and it all gets very messy. It's brittle, it's not very good. So the obvious approach, once you start to learn about these things, is to say, well, okay, let's create our thing called a people predicate. So we create an interface now, which allows us to define a method called satisfies criteria, which takes a person as an object. And that way we can say, okay, if I want to use that, now I just want to print people based on some predicate, which is my people predicate, and if it satisfies their criteria, that we print the person. That way, if I want to do older than, my predicate is one way of doing things. If I want to do younger than, I have a different predicate to define how things work. And I can do people between a different age and so on. So for example, now I get my method or class that I want to use to find retired men. What I can do is I could say, okay, I'm actually going to implement this as a class. I'll implement the people predicate interface. I've got my satisfies criteria, which is just going to test the gender to be male and the age over 65. And if that's true, returns true. Great. And then I can simply use that class and pass that as a parameter to my method, and that will match the interface because it implements the interface, so everything's good. But again, that's still not, that's not the best way of doing things. So the way we tend to use this is, as we've seen previously, we would use an anonymous in a class. So now we say, okay, we create a new people predicate as an anonymous in a class. We've got satisfies criteria. The same structure, which simply says, are these people men over the age of 65? And that matches our criteria. And as we've seen, what we can do is we can replace this with a Lambda expression. So it simplifies the code, and we say, right, now we say P is the parameter we're passing, which is the person, P.getGender is male, and P.getAge is greater than 65. So the important thing about this, which we really need to get across, is we now have parameterized behavior. We're not just passing a value to the method, we're actually passing behavior to the method through the Lambda expression. We've always been able to do this by using anonymous inner classes, but now it's much, much simpler to do it with the Lambda expression. So we have parameterized behavior, not just values. And to me, this is why Lambda expressions are such a big deal in Java. So now we can make things even more generic. So we've got our idea of the interface that we created, which is a people predicate and satisfies criteria on a particular person. But if you look in the function class library, you'll find that there is a predicate interface, which is generic, so it takes something of type T. That way we can say, okay, we've got a predicate of type T, and the method associated with that is test, takes something of type T, and returns a Boolean to say whether the test succeeded or failed. So what that then allows us to do is to say, okay, if I want to print people using a predicate, now I say, okay, I've got a list of type person, my members, I've got a predicate of type person, predicate, and then I'm just going to iterate over my collection and see whether those people match and print out the result. So now the interface here defines the behavior of this particular method. And the call to the method executes that behavior. So when I call test on that predicate, I've defined the behavior in the method, in the parameter I'm passing, and I'm executing the method to give me the particular behavior that I defined. And then when I call that, I can use my Lambda expression to say, okay, here's the Lambda expression which defines what my predicate is going to do, and so the behavior is now passed as a parameter. So this makes life a whole lot easier in terms of how we can extend our classes, how we can extend our methods, make them more generic, and do more complex things with them. So what we can also do is we can use a consumer. So again, this is from the function class library. So now we have a consumer, which takes an object of type T, and has a method to accept that, which takes an object of type T, but doesn't return anything, so it's a void. So we simply accept it or not. If we want to use that, what we can do is we can say, okay, let's extend the method we had before, add another parameter to the method, and say this time, what we're going to do is we're going to have the process people, which will take a list of people, the collection of people to do something with. We'll have a predicate associated with it, which is how we're going to test things to see whether they match our criteria. And we're also going to decide how to consume those things. And in this case, the code becomes very simple. So we say, OK, we iterate over our collection again. If the predicate returns true, to say that it matches the criteria that we have, then do something to consume that result. And that way, when I use Lambda expressions and I call that method, what I say is, OK, I'm going to process my people, pass the membership in. I'm going to use the same Lambda expression to define retired men. But this time, the consumer is to call the print stream method, print person method on that class. And if I want to change the way that works and use a different method, then print email address or something like that, very easy to do because the code is not tied to the implementation in the method. So I can also make that simpler because I can use the method reference, and now I can simply say that the Lambda expression for my consumer is to simply call print person on the person object. So that makes it even more shorthand. And then to demonstrate the use of a function where we're using a return value, what we can do is we can say, OK, again, the function interface comes from the function package in the class libraries. This has two types. That's the input type T and the output type R. That will apply, the method is apply, which will take the parameter T as type T and return something of type R. OK? And we can extend our method again. And now we've got process people with function. And we say, OK, we're passing in a collection, which is what we want to process. We're passing in a predicate to define which people we want to process. We're going to have a function which takes input of type person and returns output of type string. So it's going to do something to get strings from people. And then we're going to change the way the consumer works because the consumer is going to use the results of that function. So rather than it being a consumer of person, it now becomes a consumer of string. And then in our body of our method, we simply iterate over the members. We test to see if the predicate test is true. If it is, we apply the function to the person and return some data in the form of a string. We then call the consumer and accept that using the data which is of type string. So this is now shifting all the behavior out into the Lambda expressions that we pass in. So if I want to use that, I can have process people with function. I've got membership is my collection I'm passing in. The same Lambda expression to define retired men. The Lambda expression for the function is going to be to get their email address. So that will take a person and return a string in the form of their email address. And then the consumer will be to say, OK, that's their email address. I want to use that, and I simply want to print that email address out. And what I can do is I can then use the method references to make that simpler. And I can say, OK, process people with function, membership, the Lambda expression for retired men stays the same. But in terms of getting the email address, that's simply a method reference. So I can say person, : get email address. And I can also use system.out : print line to represent my consumer. This is where things get a little bit sort of, you have to think about it a little bit harder because you go, well, OK, system.out.println. What am I printing? There's no indication there of exactly what gets printed out. That's because if you look at the example above, it's made more obvious by having the full Lambda expression because we have email as our parameter and we say system.out.println email. But of course, if we made that E and print E, it wouldn't necessarily be obvious what that's doing. So this is where the readability of Lambda expressions means that we can make the code a lot more concise. We can make it a lot more succinct. But we need to be careful about how we use them in terms of readability. So it would be, you need to be careful about how you use these in terms of making things too succinct, because the problem you then get is you look at that and you go, well, OK, what does it do? So you then got to go and look at the body of the function in order to find out what's going on. And I'm just about to run out of time, so that's good because I'm on to the conclusions. Right, so just to conclude then, Lambda expressions allow us to define the way of passing behavior to a method and doing it in a simple way rather than using anonymous inner classes. By doing that, we can chain method calls together, we can avoid the use of serial programming versus explicit parallel programming, and by using the streams API, by using the new functions API, we can really simplify the way that a lot of the code works, and we can really use a much more functional approach to the way that we code in Java. So certainly in terms of Java SE8, there's a big change is coming, and it's worth spending some time looking at how Lambda expressions, how the libraries work in conjunction with these things, so that you can get the most out of writing the new things that you're doing in your code. So with that, thank you very much.